second speaker of the morning session today is Laurent Clozel from the Université Paris-Sud, Orsay Paris-Sud. Sud, yeah? Sud. And he will speak about author theory of automorphic forms of classical physics. This is a survey for all of us. Thank you.
Okay, well, thank you. Actually, Orsay, Paris-Sud, 11. So actually, I've been asked to give a service lecture, namely to explain Arthur's theory of automorphic forms on classical groups. So that's the first topic. And the second topic, of course, given the theme of the conference, is the relation between some of these forms, namely arithmetic or cohomological forms, and Galois representations. Okay, so I will actually explain two main points. So the first one is, again, the first one there. It's to give you an idea of Arthur's description. And what it does is that it reduces the description of automorphic forms on classical groups to forms on GLN, and those now to some extent are supposed to be understood. And our automorphic forms are numerous, but in particular what we are interested here, because that's for different reasons central in number theory, is the forms which occur in the discrete spectrum. Okay, that's the first aspect. The second aspect is that then I will remind you of the results which now have been obtained about forms on GLN. And this is known only in fields of arithmetic nature. So I'm really interested only on forms on groups G of F. I'm going to be more precise for F, a number field. And the first part of the description is correct for arbitrary F. But when we come to real arithmetic, in particular Galois representations, then we have to take more narrow number fields. So part 2, Galois representations, applies only to either totally real or CM fields. So at that point, I hope I will have explained the reduction of forms on classical groups to forms on GLN. And we now have many results on forms on GLN. So the kind of things we understand or control is Galois representations. And in a related way, we also understand purity for forms of arithmetic type. And in particular, so for GLN, this means the Ramanujan conjecture. Now, once we have this control on forms on GLN and Arthur functoriality, those results transport to the classical groups. And I will just give some examples at the end. So, in particular, results on Galois representations associated to certain automorphic forms, and well, results on purity. But of course, you will see that they have to be reformulated for classical groups in a way which is actually completely described by Jim Arthur. Now, those results are actually fairly strong, and at the end, I want to explain two puzzles. Which are related to this. And in particular, you will see that in some cases, thanks to Arthur and thanks to the progress on the study of GLN, we are getting ahead of what should be done on Shimura varieties. We are really understanding Galois representations which are there, but we don't know why they are there. So I'll try to sketch this. Okay. So that's my program. The last remark is I'm reporting on material of Arthur which is not completely written, which is now in the process of being written. But there is a survey of this, which is what I rely upon except for conversations with my friends. And that's in the Clay math proceedings, number 4 to 005. There are about 250 pages, and you have to skip to the 30 last pages. But despite what I just said, I think all the material I'm going to present is really not conjectural. Everything either is written or could be written on the basis of what is known. And in particular, I will also try to avoid metaphysics and conjectural objects, because after all, we are in Britain. Okay, so let me start with Jim Arthur. So this is really propaganda. I want to try to show you that Arthur's description is really understandable. So F is a number field, arbitrary so far. And G is going to be a classical group over F. And so far, I'll take G quasi-split. I'm not going to define quasi-split because I'm going to give you the list of groups we are interested in. Let me start with SO2N. So a classical is really restrictive. It means it's exactly the groups I'm going to mention. And remember that in Langland's theory, we have a dual group associated to a group over a number field, and I give you the list. So here the dual group is isomorphic to G. Okay, so this is just a complex group. What does this mean? What does it mean for G to be quasi-split? Well, actually, here there are two possibilities. Either G is split, and think of SONN. It's the group of a quadratic form which actually has a maximally isotropic space, or a quasi-split but not split. And again, think of SO n plus 1 and n minus 1. So it's a group which has the next possible index of isotropy. The next groups are in my order SO2n plus 1. In this case, the dual group is a symplectic group. I write SP2n despite French usage. This is the dimension of the space. And of course, conversely, we also have the possibility that G is SP. This is, of course, a split group, naturally, and G hat then is SO2n plus 1. You see, Langland's duality is symmetric. Okay. So we are going to be interested in automorphic forms on those groups, and so far with no arithmetic condition. So first of all, note that all those groups are semi-simple, and this means that if I write A for the adels of F, then I can form G of AF divided by G of F. This has a natural measure for which it has a finite volume, let's say volume 1. And then it's natural to consider the L2 space for the invariant measure. And on this, I have a representation of the adels group. So from now on, I'll drop the F here. And just by general principles, if you have a group, a locally compact group acting on some Hilbert space, you can isolate the discrete part. And this is it. It's the sum of the discrete summons. Now, actually, this is not important because by Langland's theory, once you have described the discrete part, you actually know all the rest. So our problem is for all those groups to understand this discrete part. So it's quite spectacular that Arthur does this. And he does that by starting with the elementary building blocks, which are cuspidal representations for GLN for all n's. I haven't listed GLN in the classical groups because this part of the story was known for a long time, actually due to the efforts of Meuglin and Valls-Purgé. But I am not going to describe this because I don't need it. On the other hand, I have to explain what the atoms here are. So, of course, we can form the same space for this group, call it, say, G tilde. And then I have the space of L2 functions. Now GLN has a center, so this is not quite a good object. The volume will not be finite. So I quotient on the right or on the left by something in the center. So R star plus is contained in, sorry, this is F. This is contained in the dels, and this is centrally contained in G tilde of A. Okay, the whole point is to make this a space of finite volume. And then it makes sense to look at the discrete spectrum. But in fact, the building blocks are not all the representations in the discrete spectrum, which are already complicated. The building blocks are the cuspidal representations. So the cuspidal representations of our group GLN. So if you take this space of L2 forms, there is a space of cusp forms. And I'm not going to write the formula, but this is a space analogous to the classical cusp forms for GL2. Since part of the result is that it's contained in this, it decomposes discretely. So this is an infinite but discrete sum. And what else do I want to say? Yeah, moreover, those representations occur in the total space with multiplicity 1. In fact, there is more. There is something called the strong multiplicity 1. But I'll mention it in a little while when I have the notions to explain it. Okay. So in any case, what matters is that these are the representations with which we want to describe the general forms on classical groups. Whether we know what they are is, of course, a matter of taste, but a lot of properties are understood. Okay, so now let's go back to a classical group. And let me just explain to you what description Arthur gives. And this description is by something that we call Arthur parameters. So let's go back to G in my list of classical groups. And as you saw on the right-hand side, the dual group is always contained in a tautological fashion in some GLN. And this n I will call the natural degree for G. Okay. So, natural degree and the natural dimension. And then I want to describe an outer parameter, to define an outer parameter for G. But first of all, let me define an outer parameter of degree n, capital N. This is just a formal sum, psi, say from 1 to R, of, well, formal ingredients, the first of which is a cuspidal representation, mu, and the second of which is actually just a number, but let me explain to you how we think of it. So here, this is related to a decomposition n as a sum from 1 to R of mi, I follow Arthur's notations, and ni, so a partition of that type. And as I said, mu I is a cuspidal representation of GL mi, of course over the adels of F. And nu I is just a number, but we think of it as the corresponding representation of SL2C of the right dimension, namely Ni. Okay, so this is an Arthur parameter, and the condition we will impose in all cases is that psi is self-dual, so we assume psi self-dual, which means that formally the collection mu I tensor nu I is the same as mu I Czech tensor nu I Czech, the dual, but of course a finite dimensional representation irreducible of SL2 is isomorphic. Sorry, I didn't say this here, but nu I is the irreducible representation of degree Ni. Okay. Okay. So this means that the global collection is stable by passing to the dual, and taking the dual acts only on the first components. Note that, of course, it makes sense as a representation of a GL Ni A. This has a dual, and which is also cuspidal. Okay. Sorry.
MI should be N, right?
Where?
GL, last but one line. First line of the last ball.
Oh, this, yes, thanks. This is mu, yeah. Okay. Okay, so these are the general parameters which will interest us, but we now want to narrow down this collection to define Arthur parameters for G, where G is one of my lists. So 2 Arthur parameters for G. So G is given of the right degree, but in fact what I'm thinking of is not the group itself, but it's a dual G hat in GL NC. And I want to say what it means for a parameter to be of type G, but in fact the parameter should be thought in the dual picture, and the conditions are imposed by G hat. So remember, this is essentially an orthogonal or symplectic group. Okay. Well, let me give you a definition. So first of all, I say that psi is of orthogonal type or respectively symplectic if and only if well, there will be components of psi which are paired to something else, but the things which have to be paired with themselves have to be of the right type. So the correct statement is this. Each summoned mu I tensor nu I either occurs with its dual or is a self-dual. That's forced actually by the first condition. And of the right type, of orthogonal. Or respectively symplectic type. Okay, that's a good definition, but of course I haven't told you what it means for the individual summons to be orthogonal or symplectic. And let me contract two definitions in one. So what does it mean? Well, we have something that we think of as a tensor product, where there is a representation of SL2 and the original cuspidal representation. Well, here we have a finite dimensional representation of SL2, and of course the sign of its duality is uniquely fixed. Nu is, for example, orthogonal as an irreducible representation of SL2 if and only if its dimension n is odd. And of course it will be symplectic if and only f is even. Now, of course, if I want to decide whether the unique abstract hypothetical duality on the tensor product is symplectic or orthogonal, once I know the sign on this factor, I just have to know the sign on the GLM factor. And so what does it mean for mu to be orthogonal or symplectic? Well, this is more delicate, and in fact it will play a role only at the end of an intricate induction of Arthur, but it's easy to define. Remember that mu is isomorphic to its dual. It's a cuspidal representation of GLM. And for two representations of GLM, there is an L function of pairs, L of S, mu tensor mu tilde, which is the same as L of S mu tensor mu. And it is known that because we have mu tensor mu tilde here, this has a pole over the 1 at s equal to 1. So this is, of course, the Rankine L function in this context. And on the other hand, as I said, it has a pole because of this expression, but it is also this. And as such, it decomposes. If I write L of S mu tensor mu, it decomposes. This is all effective, although I cannot explain why, but there is a part associated to the exterior square, and then there is a part associated to the symmetric square. So since I have a pole over the 1 in total, you see that one of those L functions exactly has a pole, and that determines what I need here, the sign of the representation mu. So the factor where the pole occurs determines the sign or the parity of mu.
All these L functions are known to exist.
Sorry?
All these L functions exist and extend.
They are all known to exist, yes, and to be holomorphic at least.
Holomorphic, that's a
No, at least where I won't guarantee this, but at least where we are computing and so on, yes. Probably everywhere here, but yes. So, no conjecture.
So I was checking you up.
Okay, so I hope this is reasonably clear. So I have a family of parameters for G, and the last thing I want to specify is which parameters should be discrete. I really want to describe only the discrete part of the spectrum, and clearly this means that we should impose a condition of the same kind on the parameter. And in fact, that condition is fairly easy to understand. Look at the decomposition here, and suppose, for example, that all factors are, say, symplectic. If two factors are the same, I can twist one by the module to the s, or an artin character if you want, and twist the other, and so in so doing I can deform the two parameters, in fact, continuously, and get a family of parameters for the whole group. This won't do because I want something which is discrete. So what I'm forced to do is to assume that each factor here has to appear with multiplicity 1. Okay, so that's the last part of the definition. So finally, discreteness forces the really quite intuitively obvious condition, each factor mu tensor nu, which has now the good parity by assumption, occurs with multiplicity 1. Okay, well, that's it. That's the definition of an Arthur parameter for G.
So it has to be symplectic or orthogonal according to what? Whether G dual is symplectic?
It's all in the dual, yes, of course. I said it, and you know it, and I insisted on this, yes. And so this defines an Arthur parameter for G. So the parity is the parity of G hat. Okay. Well, actually, now it's fairly easy to state the theorem and not to prove it. But I'll give you a rough version of Arthur's theory. And probably I'll stop there for the representation theoretic part. The last thing we have to do is to describe a way to nail down a representation of G given an Arthur parameter, and this is done using Hecke matrices. So I'm going to describe this with the exception of one case. Let's just forget about non-split SO to N, because what I'm going to describe here is more complicated. But let me describe the split case. What we do here, what we have here is a group G, and we have its dual G hat, which is contained in GLNC. Now suppose I have a representation pi of adelic GA, of adelic G, And remember that this is essentially a product. This is a restricted product of G of Fv over all primes. So representation pi is determined by its local factors. And pi v will be unramified almost everywhere in a natural sense. And the theory of Saclay actually in this situation associates to it a matrix in the dual group. So if pi v is unramified, we have associated to it a matrix in the dual group. And in fact, we can take a diagonal matrix. Okay. On the other hand, of course, the datum, the parameter psi, under the duality assumption, so self-dual of the right type, also determines an element T psi v, which a priori is contained in GLNC. But in fact, since it's a diagonal matrix, we may as well think of it as an element in G hat. Of course, the matrix will have to satisfy the conditions which are true for a diagonal matrix in the orthogonal group, for example, but that's the case. Now, I didn't say how this works. That's not obvious. We have a decomposition of psi. We have factors of this type, and we assume, of course, this will be true almost everywhere. We assume all mu I unramified at V. So remember, these are cuspidal representations of the right dimension. And then they have a Hecke matrix, T mu I V, a matrix, of course, of dimension n mi. And then I can write a formula for this. T psi v is a sum with diagonal blocks of T mu I v. And then there is a tensor product by a fairly important diagonal matrix which comes from mu I, and this is qv to the ni minus 1 over 2, and so on. I just shift the exponent by 1 until the negative exponent qv 1 minus ni over 2. Okay, now I have said everything. You will check that with the correct assumptions. This parameter has the duality properties to define a Hecke matrix, not for GL, capital N, but for G. And that defines, again, the local unramified representation. So the thing to remember is that psi defines for almost all V a local unramified representation of G.
Can the conjugate classes split in G?
Sorry?
Conjugacy classes, semi-simple conjugacy classes in GLN are diagonal matrices. But in G dual, can they somehow break further? Have you really defined one semi-simple conjugacy class in G
or the choices?
Yes, except for it takes a grain of salt for SO2N. Okay, but I won't explain to you. Not now. Okay. A slight correction for SO2N. I always put aside the non-split case, but there are problems with respect to this even in the split case. Okay. Okay, in any case, the basic idea is correct. And let me now state a theorem. So this is really due to Arthur. So let me give two statements which are relatively weak compared to the whole theory, but I think you will agree that they are already impressive. So first of all, if pi occurs in L2 discrete of G of f mod G of AF, okay, there exists an Arthur parameter psi, which is what I define with no ambiguity and no assumption for G. Psi will be unique modulo, of course, the obvious equivalence that you can cook up, and such that for almost all primes, the Hecke matrix of pi at V is the thing that I wrote up there, psi V. Okay. The theorem is much stronger, but let me just state weak converse. Conversely, any Arthur parameter psi occurs in that sense in L2 of G. Okay, so I had wanted to be more explicit, but if I do that, I will not be able to get to Galois representations. So let me just say a few words. This, of course, gives you already a fairly strong handle on the representations which occur here, but the theory is much more complete. In Arthur's theory, we are actually able to describe all possible local components of the representations pi, including what occurs, the ones which occur at the ramified primes. This is due partly to Arthur and partly to the elaboration on his results, which has been made by Meuglin and Walsburger. So I think when Arthur's notes come out, in fact, based on earlier work, we will actually know. Sorry?
For some pi. First for some.
Oh, pi, thanks. So we actually know much more. We know all the local components. Yes?
Maybe it's a very naive question, but is it possible to interpret this theorem as an instance of functoriality?
Yes, of course, but that's precisely what I wanted to avoid doing. But yes, I'll tell you at the end. Yeah.
So it's very difficult.
But do we have functoriality? Can we form ui tensor ui?
At the end.
Okay.
Let me go on. So that's the part. That's part one, and now I want to get to progress for GLM. So in Arthur's results, the building blocks, the mu, are taken for granted. But on the other hand, the last 20 years, we have made a lot of progress in understanding those representations. at least in the arithmetic case. Now, arithmetic here means the following in this talk. First of all, I assume that f is totally real. And then I'm going to consider a cuspidal representation, which I now call pi. And I will assume the second assumption is that this is of arithmetic type, which is expressed in terms of the Archimedean factors of pi. So for a prime dividing infinity, then pi v is cohomological. For some system of coefficients, I will not explain this, just take it as a black box if you don't know it. But the point is that the system of coefficients is associated to an n-dimensional, to a representation of GLN, okay, associated to an algebraic representation of GLN.
Depend on V.
Sorry?
Can it depend on V?
Yes, anything. But the point is that you must have a tal cohomology. Okay. So these are strong conditions. If you see what, if you make the computation for GL2 over Q, for example, this means that you are considering classical forms of even weight. So let me now state a theorem under those assumptions. Theorem 2. First, there exists a number field E and a compatible system of lambda-adic representations lambda runs over the finite places of E. Of
duality?
sorry?
You don't need a duality?
Oh yes, I'm sorry. Actually, of course, all my representations are self-dual here, but I should recall it. So assume
Get back on my chair.
is isomorphic to its dual. Yes, thanks. And a compatible system of lambda-adic representations of the Galois group. Such that, well, let me just write something and explain what it means. What I will have is that, let me just state the rough results here, because otherwise I will not have time to explain the puzzles. So for almost all V, in particular, I can assume that those are unramified. Then we have the following. P of T pi V. This is the Aker matrix, which I did not mention, that I did not define, but which I mentioned for GLN. This is its characteristic polynomial. And what I'm saying is that this is the same as the characteristic polynomial of R lambda. So R lambda is the representation associated to the Frobenius, applied to the Frobenius at V. And then there is a twist, which is QV to the 1 minus n over 2. And I take again this matrix, now in some lambda-adic field, and its characteristic polynomial. Okay. It will also be known how the representations behave at the finite prime, at all primes, but I don't want to write it. The last thing which I want to write is that the representations R lambda are pure of the right weight of weight n minus 1. Okay. So, this will be true for V, of course, prime to lambda, where we are working with the lambda-adic cohomology. Okay. I think the statement is self-contained, but let me just say one extra word. So here we have the representation of GLN, satisfying, of course, a lot of conditions. We have its Hecke matrix, which determines the local component. And the theorem says that actually this Hecke matrix corresponds, or their collection corresponds to a collection of Frobenius elements in Galois representations. This theorem actually is not in the literature. It's a part of, it's the result of the efforts of a lot of people, including Kotwitz and myself some years ago. And the work of Shin about proving the thing I have not mentioned here, the precise correspondence. What I should say is that in some cases, actually, the theorem is not in the references I mentioned here for singular parameters, but in fact, I convinced myself recently that it did extend to the general case, and then I found out that Richard Taylor had been aware of this for several months. Okay. Okay, now we'll just use this, and let me go back to the consequences for classical groups. And in fact, I'll skip some of what I wanted to say because I mismanaged my time. But I want to insist on the amusing things which are the puzzles. Now, the first thing is that if you go back to this list of classical groups, those groups, or some forms of them, will be associated to Shimura varieties. The obvious example is, of course, SPG, which defines a Shimura variety, which is the space of principally polarized abelian varieties. But there are more amusing ones. So G or some inner form of G is associated, will be associated to a Shimura variety. So I must state the typical example, which of course is SPG. I wrote 2G, so let me stick to this. Let me take Q as the ground field. And this, of course, has a quotients, arithmetic quotients of the symmetric space, which are associated to AG, moduli space of principally polarized abelian varieties. So in this case, in fact, using the results on GLN and transporting back with Arthur, we obtain information on forms here, which is more precise than the realization of the corresponding representations in the Shimura variety. I don't want to detail this because I want to come to my two puzzles. So let me give you another example. We can work with SO 2n plus 1. Okay. I just write this because I'm going to specify a rational structure. So a priori, this is described by Arthur in the quasi-split case. But of course, this has inner forms which are not quasi-split and which are therefore more interesting. Namely, I can impose at infinity. So let me take a group over Q, say, such that G over R becomes SO of 2n minus 1 and 2. And of course, the particularly nice case is n equal to 10, which gives you the group SO19 2. This has a Hermitian symmetric space. It's associated to Shimura varieties. And for a suitable form of this over Q, the quotient describes the moduli space of K3 surfaces. So the arithmetic quotients give you the moduli space of K3 surfaces. Of course, this is just a particular case which is remarkable because it's classical, but we can look at all groups of this type in all dimensions. So moduli space of K3 surfaces. This is a space of the dimension 19 over C. And what is the puzzle? Well, the consequence is that, first of all, there is a conjectural description of the number of points so called the moduli space S over finite fields so this is due to Langlands and Kottwitz. 2, if you believe this conjectural description, and if you use Arthur's results, you can actually write the assevate zeta function in terms of automorphic forms. So L functions of automorphic forms. 3, because of functoriality between this group and GLN, all these the associated Galois representations exist. So that's essentially because of the previous arguments. And so we are in a situation where we have this algebraic variety we can write down what the associated Galois representation should be, but actually we do not know that description between the number of points and the automorphic data is correct. So nevertheless, we don't know that this data function that we can write explicitly, for which we can prove a meromorphy and so on, is the right one. Okay. So from this and from the example of SPG, which I did not make explicit, what you see is that thanks to Arthur, somehow we are getting ahead of what was expected from the Shimura varieties. We are not only constructing automorphic forms, but also Galois representations with all the right properties associated to the cohomology of varieties for which we cannot count the number of points. So of course this is a puzzle, and it means that there is really work to be done for the varieties for which we do not have a description as a moduli space of abelian varieties. Okay, I wanted to describe a last point in order to be agreeable to Kevin Buzzard, but I think I'll stop here.
Does by now really exist a complete conjecture what the zeta function of Shimura variety is in all cases? Is a complete conjecture now?
No, I would not say that for unramified primes. This is explicit. I think it becomes explicit only in the cases which are proved. So what I mean is that in the case of Harris-Taylor, and also in the case which has been studied by Shin, you provide a description of the local model which tells you what the local Galois representation should be. And in the cases where you can do that, you actually prove it. But I would not, I'm not an expert by the way, but I would not say that, for example, in this case, people have this for those particular varieties. The description of the local model actually depends on the fact that you have a moduli problem.
Right. No. But my question was if there's a prediction, I mean, by Langlands and others.
Yeah, the generic prediction is that it's always given by Langlands, of course. Yeah. And you see, a posteriori here, everything is determined. I mean, once we have all the work which is not published. But for example, let's take this case. There is something I did not explain. It's going from the non-quasi-split group to the quasi-split group. But this is well understood. Okay. So what will be the situation? We start with the representation of SO2n minus 1 to the non-quasi-split group, non-split. We will know what the local component of the image on the non-quasi-split group, on the quasi-split group is. We will know what its image in GL here 2n is. Actually, this is already largely done in the literature. Guy can correct me. So we know the local component at the level of GLN, and then the correspondence tells us what the local restriction of the Galois representation is. So the answer is yes. So this is really a propaganda talk in the sense that if you have a problem which relies on this kind of things, the detailed information is going to become available.
Maybe I just want to make sure I understand the puzzle. So I guess the thing is, you have the zeta function of S, which can be written in terms of automorphic representation of SO 19.2.
It could be if we
It's a
know.
conjecture of language.
Yeah, if we knew that
Yeah,
the
if
counting
you
of
knew
points
that,
corresponded
so
to.
that part
Yeah,
would be conjectural. But then by Arthur's parametrization, this can be written in terms of automorphic forms on
JLN.
JLN.
That's
But
right.
you don't know that this latter thing fits the zeta function of the thing that you
It's
started.
the first step. You don't know how to count points. You know the conjectural
The
answer. but-
ridiculous thing is they can construct the Galois representation.
So it's not
They
clear it
haven't
has
proved
that-
that it's there. They can construct the étale cohomology. They can construct something that should be the étale cohomology without proving it is. And normally it's the other way around.
It should be
No-
the
normally-
homology of S. You mean, but-
Yeah, it should be the étale cohomology of S. But you just can't.
I should say I haven't been precise here, and I don't want to say more, but there's just a very tiny bit missing. Namely, you want, of course, the correspondence of Robéniaï, but you also want the correspondence of the local representations, the local factors of your given representation of GLN and the local Galois representation. And of course, this again, there is a hierarchy of things. You could want the traces of the semi-simplification, or you also want to control the unipotence in the veille de ligne group. In the most singular cases, for the highest weight of the coefficient system, the only thing which is missing is the control of the unipotence.
So that Taylor Yoshida didn't do that.
No, it's in the situation of, so it's not done.
Comparability when the places divide lambda, so easier.
Say that again?
Oh, when V divides lambda.
I didn't say anything, and I don't want to say anything.
Is
But-
something no?
I mean, except the obvious things. If it's
Turns out it's
unramified,
Taylor.
the representation will be crystalline.
But this is known. Even
This
in
is known. It's
even without the supercuspidal plate.
it's almost. It's probably almost on this side. Yeah. But the last singular case here, the last straw is not written, but I'm not really convinced.
And it's known to be Durham in general.
Sorry.
It's Durham in general.
I think the local p-adic properties here were already done. They are in the paper by Harris and Chalelier. But
So is there an Arthur parametrization for non-split classical groups, or maybe something that's maybe not even a classical group, but for example, trilitarian D4 or something?
no. First of all, I'm really talking about classical groups. So, for example, the spin groups are certainly very interesting, but they are just not covered by this. The second thing is that, as I more or less alluded to here, once you have the theory for the quasi-split group, the rest is actually, for the rest, you are reduced to things which are already known. It's the stabilization of the non-twisted trace formula, which has been done by Arthur. So once your problem is well posed, you can actually prove it. You can control the representations. It may or may not be in the final write-up of Arthur, but in any case, for any specific problem, this is not accessible.
So that's for inner forms?
That's for inner forms. Now, actually, I'm particularly interested in the D4 associated to triality, but I will not give you the answer here.
Okay. So since there are no further questions, so let's thank the speaker.